Alright, in this video we're going to take a look at finding the domain of logarithmic functions. So up until now, the only domain restrictions we have had have been that the denominator, if we have a variable in a denominator, that the denominator is never allowed to equal 0, and we can't take the even root, such as a square root, fourth root, sixth root, etc., of a negative number. In this section, as we've seen, logarithms have a domain restriction, and that is we can only take the logarithm of a positive value. So whatever we're taking the logarithm of must be greater than 0. So whatever we have here, especially if we have a variable, that means that what is essentially inside these parentheses, we're going to set greater than 0 and solve. So example 2, find the domain of each. Write your answer in interval notation. So we have f of x equals 2 times log of 3 minus x, and then after that, minus 1. And I do want to point out that it doesn't matter if the base is a positive number that's not equal to 1. The logarithm's domain, regardless of either of those bases, is always going to be greater than 0. So we have a 3 minus x that we're taking the logarithm of. That 3 minus x must be greater than 0. So subtracting 3, dividing by negative 1, we're going to get x is less than 3. So we can put in any number we want into this function, and it'll give us back a number in return as long as the number we put into the function is less than 3. So negative infinity, comma 3 with parentheses. The graph of f of x we have right here, and I'll just attach the vertical asymptote here. So that domain is stopped by the vertical asymptote. Notice all of our values of x are less than 3, so like 2.925, 0.9, negative 4.54. All values on this graph must be less than 3. Part B, we have g of x equals negative 2/3 times log base 8 of x squared plus 6x minus 7. We saw in polynomial functions how to handle something like x squared plus 6x minus 7 greater than 0. So with x squared plus 6x minus 7, if we set it equal to 0 and solve it, we're going to get our critical values at negative 7 and 1. So setting up our number line, we cannot have them equal negative 7 or 1, because then we would not be taking the log of a positive number. So with logarithms, especially, any of those critical values you get are going to be automatic open circles. So we have negative 7 to 1. We have an interval less than negative 7, between negative 7 and 1, and greater than 1. When we test out values in the original problem here, the only ones that won't give us any kind of error messages are the ones that are less than negative 7 or the ones that are greater than 1. So if we tried a number that was in between negative 7 and 1, let's say 0, we'd get negative 2/3 times log base 8 of negative 7, and that's an imaginary number. So the solutions to this problem in interval notation are less than negative 7. This should be a negative infinity. I apologize for that. Less than negative 7 or greater than 1. So negative infinity and negative 7, unite that with 1 to infinity and parentheses. So again, I apologize for not having the negative there, but it should be a negative infinity, comma negative 7. All right, part C, we have h of x equals the natural log of x over x minus 1. We want x over x minus 1 to be greater than 0. It's really nice that our critical values, we can just set x equal to 0 and x minus 1 equal to 0 with rational inequalities that have a 0 on the right-hand side. So our critical values on our number line are going to be 0 and 1. We know that we cannot equal those because we cannot have the natural log of 0. So open circles at 0 and 1, and the values that will make them true are less than 0 or greater than 1. So we have negative infinity to 0, and we're going to unite that with 1 to infinity, and once again parentheses all around, because we are not allowed to equal 0 and we are not allowed to equal 1. All right, so that about does it for this video. Thanks for watching, and I'll see you